Hello, Mrs. Buckholt's class. This is Mr. Morris downstairs in room 150, and I get the pleasure of creating a lesson for you guys today because Mrs. Buckholt couldn't be here. So she asked me to kind of go over this example and focus on helping you learn how to solve these kind of problems using your graphing calculator. So that's what I'm going to do. All right, so this is chapter 5.1 in the Carnegie books. All right, so bear with me. I haven't seen a Carnegie book in about 2 years, and I have successfully stayed away from them. So this is new territory for me, but I think I've got it for you. All right, so we're looking at this example here. So the Plant A Seed Company is producing planter boxes. So these are boxes that you're going to put in some sort of flowers in or something that might be out in front of a store. So to make these boxes, a square is cut from each corner of a rectangular copper sheet, and the sides are bent to form, not from, a rectangular prism without a top. Cutting different sized squares from the corners result in different sized planter boxes, and then Plant A Seed takes sales orders from customers who request a sized planter box, so specific to whatever their needs may be. All right, so basically we're looking at this shape here. Right, so we're looking at this sheet of copper, and we're going to cut these little corners out, if you can visualize this. So these are going to be gone. And you can kind of cut them to whatever shape, and then you're going to fold these sides up so that we get some sort of planter box maybe looking like this. All right, where this is going to be my height h all the way around. All right, so the first thing that I'd like to look at here is what is the largest size square corner that could be cut to make this planter box? Well, it can't just be anything, right? Because I'm going to be cutting off these little squares. They're not infinitely large, and I am going to be cutting something off, but at some point it's got to stop. And what's going to limit it is actually your short side. So a lot of times when I ask my students this question, they always leap to it and say, oh, it's 12, because that's the smallest number. And it's actually a lot smaller than that. It can't be 12, right? Because I'm cutting it from both sides. So if I'm going to be cutting a square here, then I also have to be cutting a square there. So I'm never going to be able to cut the whole thing. That just doesn't make sense. So what this is going to end up being is actually 6, right? 6 across, because I could make the square cut from here and then from there. Now, that's not really going to help me in creating planter boxes because I will not have any copper sheet left to make a box, but that is the absolute most that I could cut. I could do the same thing with the 18, but it's by the time I got to 9, I would already have overlapped on my short side, so that doesn't really make any sense. So it's always the smaller of the two sides that's the limiting factor here. So the largest square corner that I could be cut from this planter box is going to be 6 inches. All right, so if we had to write a function for the volume to represent this planter box in terms of the quarter side h, so it's going to be v of h. I can only have a volume function using h's. Well, we know that the volume of a box is going to be length times width times height. Right? Well, in our case, if we take a look up here, whenever I do problems like this, I always kind of look at these two pictures together and try to figure out what this distance is going to be and what this distance is going to be. I already know that the height is going to be h, so I can leave that as part of my formula. So when I come down here, the volume with only h's in it is going to have this h, right? It's the length and width that's going to be changing. All right, so when we come back up here and take a look at that, well, how wide is this side here going to be? Well, if I had 18 inches all the way across, and I'm going to cut this part off of it and this part off of it, well, each one of those is h wide, So I'm going to be left with 18 minus 2h. And then the same thing's going to happen on the short side. There I'm going to get 12 minus 2h because I'm taking an h and an h off of this one. So we're really just kind of calling these inside parts what they are. This is my 18 minus 2h because I had the h here and the h there. And then from here to here is going to be 16 minus 2h because of that h and that h. All right, so that's going to be my volume. So I come back down here and fill this in. My length is going to be 18 minus 2h, and my width is going to be, what was that, 12 minus 2h. And then times my height of h. And this is going to be my volume formula for that particular planter box. All right, now we can do some stuff with this. And this is where the calculator comes in. And this is on page 319. I didn't copy down all of these problems because I didn't think that they were all pertinent. But I did write down some of the ones that I thought were important. So the first thing we're going to do is we're going to graph this function. All right, so if I plug that into my graphing calculator into a y equals, I can type it in exactly the way that it was before. So it's going to be 18 minus 2x, which is going to take the place of my h. We're going to go 12 minus 2h, and then times h. All right, now if I just hit graph and I've got my normal graphing window that's negative 10 by negative 10 and negative 10 by negative 10 and the x's and the y's, we get this. And that's sort of helpful, but you can't really see what's happening with your graph. So your book suggests that we change the window so that it's negative 10 to 15, and then your y values are negative 400 to 400. I'm not crazy about those window settings myself because I understand that not all of those things can make sense. When you're thinking about what we're plugging in for x actually represents the height of your planter box. Well, if we're talking about a distance can't be negative, right? Despite what you might have learned in Ferris Bueller's Day Off, right? If you take a car and you jack it up and you run it in reverse, it does not make the odometer go down. Right? There is no such thing as negative distance. Right? All they were actually doing in that movie was doubling the mileage on their car, making it worse. Right? So the negatives really don't make sense, but for the purposes of following along with your book, we'll talk about where the negative stuff doesn't make sense when we take a look at the graph a little bit. So when you need to change a window setting, you hit the window button up here in the top row. Right? Hit window. All right, and now you get this window setting here, and you can change it to whatever you want. So my x minimum is being negative 10. That's fine, but we're going to arrow down here to x max, and we're going to make that 15. We're going to let the x scale remain to be 1, but we're going to come down here to my y minimum, and we're going to make that negative 400, and we're going to arrow down to my y max and let that be a positive 400. We hit graph. Oh my gosh, that's so much prettier. All right, so here's this graph, and it's got this nice wave to it, and we can find all sorts of stuff now. So the very first thing, and I kind of wrote down key characteristics, x-intercepts. All right, now you can just, this graph is so nice that you can actually look at it and you can just pick them, right? You can see that it's crossing at 0, looks like it's crossing at 1, 2, 3, 4, 5, 6. Also looks like it's crossing at 9, okay? But if you're not sure, or if you had to zoom out so much that you really can't see the hash marks, like on the y-axis, it's really hard to see the hash marks because there's supposedly 800 of them there, right? So if that's a challenge for you, you can always let the calculator do the work for you and find the intercepts, right? I wrote in here that x-intercepts are also the same thing as zeros, because that's what the calculator is going to call them, right? So I'll show you how to find these in a couple different ways. So all you have to do is to let the calculator do the work is you've got up in this top row of your graphing calculator, you see it says stat plot table set, format, calc, and table, right? Those are actually the second functions to the y equals, the window, the zoom, the trace, and the graph buttons, right? So if I hit second and I hit trace, which is really calc, right, to let the calculator do some calculating on its own, right, it brings up this, right? And what I want to find are zeros. I want to know where are my x-intercepts, so I hit 2. All right, so then it brings you back to your graph, and it's got this little cursor, and the cursor is going to stay on your graph no matter where you arrow it, right? So what you want to do is you want to arrow it, so down here at the bottom it's asking for a left bound, right? So what that means is it wants you to arrow over to the left of where it looks like it crosses the x-axis. So I'm going to arrow down here just to be safe, and then I hit enter, right? So if you're using a TI-84, I don't think the TI-83s do it, but the TI-84s put this nice little dotted line in there, so it sets, all right, we're not going to test anything to the left of this, everything's going to be to the right of this little dotted line, right? Then you'll see down here at the bottom, it doesn't say left bound anymore, it says right bound, right? So now I need to arrow over to the right of where it looks like the graph crosses my axes, and then I'm going to hit enter again, and it puts another fancy little dotted line there. All right, and then it says, do you want me to guess? And yes, calculator, I would like you to guess here, right? Because it's not going to be that much of a guess because you're a calculator, you're infinitely good at this, right? So we're going to hit enter one more time, and what it does is it estimates where it thinks it's crossing that x-axis, right? So this one's pretty good. It says x is going to be 0, y going to be 0, which is good because that's what we said. We thought it looked like the origin, and that's what it's telling me. So it's crossing at the origin. All right, I'm going to take this little guy here, bring it down into my notes. All right, so there's one of my x-intercepts. All right, so let's practice doing that again, except this time we're going to have it calculate the one that looks like what we think looks like a 6. All right, so again, you go second, calc, I want the 0, and I'm going to arrow over. It wants the left bound, so I go over here to where it looks like it's to the left of where it's going to cross. I press enter. And then I'm going to arrow over to the right of where it looks like it's going to cross. And I hit enter. And then I enter one more time to guess. And it says 6, 0. All right, so we were right on our estimation. All right, and then one more time. Take a couple minutes and see if you can't do that one on your own. Remember, it's second, calc, 0. All right, find your left bound. Enter. Find your right bound. Hit enter. And tell it to guess. See if we were right when we were saying that it was going to hit at 9, and I think you're going to find that that is what we find. And that is what we get. All right, what you want to make sure that you don't do is that when you're picking your left bound and your right bound is that you don't include more than one place where it looks like it crosses, because then it's going to get kind of confused. And my guess is that the calculator is just going to pick whichever one it sees closest. So here we got 0, 6, and 9. Right, y-intercepts here is pretty easy because it did cross at the origin. So obviously that one's going to be at 0. There is no way to calculate y-intercepts on the graphing calculator, so that's going to be one that's a little bit harder to do with calculator help. Fortunately, we know another way to come up with y-intercepts. We would have just taken that function, and you find y-intercepts by letting x equal 0, right? So remember our function was 18 minus 2x, 12 minus 2x times x, and I would just plug in 0 everywhere that I saw an x. 2 times 0, 12 minus 2 times 0, times 0, and it doesn't really matter what I get in these parentheses because I'm going to have 0 times stuff, and 0 times anything is 0, so that just shows that it has to be this one. All right, now as far as maximums and minimums go, we can absolutely do that as well. We can let the calculator do all the work. So again, we're going to go back to here. So we're talking about relative maximum. So that's places on the graph where it stops moving up. So the graph ceases to increase and then begins to decrease. That's the definition, the formal definition of a maximum. Likewise, for a minimum, that's where the graph ceases to decrease and begins to increase. Right? So peaks and valleys, right? Peaks being my maximums, valleys being my minimums. So as far as the graph goes, it makes a lot of sense. You can kind of look at them and you can see them. But as far as calculating them, they're not as easy as the zeros, right? Because especially on the left-hand side, like coming up with that y value, that's going to be quite the challenge, seeing how it falls in between 0 and 400 somewhere. Good luck estimating that, right? But the calculator can do it for us. So you do it the same way that we did with the zeros. You go to second, you go to calc, and this time instead of hitting 2 for zeros, I want to find a maximum. So I'm going to hit 4, right? And now I arrow over. Again, it wants the left bound. So I arrow myself over to the left of where it looks like it tops out there, right? I'm going to hit enter. And then it wants a right bound, so I arrow over to the right where it looks like it's going to top out. I hit enter, and then I hit enter one more time to tell it to guess. And this time the numbers were not nearly as friendly, and it came out to be 2.35 and and then my y value was 228.2. Right, so that one was not nearly as friendly. Right, so my maximum here is going to be at 2.35, and my maximum will be 228.2. Right, likewise, we can find the minimum. We go to second, calc, and I go minimum, so that's 3. And I arrow over here, left of where it looks like it bottoms out, enter. Right bound, I go to the right of where it looks like it bottoms out, enter. Tell it to guess, enter. And this time it comes out to be the 7.6, and the y value is going to be negative 68.2. All right, so we can bring that one down here too. All right, so my minimum is going to be at 7.65, and that minimum will be negative 68.2. All right, so this is kind of helpful. Calculator can do a lot of work for you, especially on these really challenging graphs where it's really hard to see what it looks like and come up with the value. All right, so your book was also asking for the domain here. So the domain is what all the x values that we're allowed to have here. So graphing calculators are really bad at arrows, but what's happening on all of these graphs, they all look the same, is I actually have arrows going that way and this way on forever. So the domain for this one is going to be from negative infinity to positive infinity, because even though these arrows are going primarily down and up, but they also are going left and right. It's just going to take them a really long time to get to negative infinity and positive infinity, but they are headed there. And then obviously the range, that one's a lot easier to look, more obvious to see here. So this one's going down forever, and this one's going up forever. There's no gaps in there, so this one is also negative infinity to positive infinity. All right, so I thought that part E here was actually a good question in your book. It said, what do the x-intercepts actually represent here? So don't lose focus of what we were actually trying to do here from the beginning. We were calculating the volume for these planter boxes, right? So your x value was represented h, so that was the distance of the little squares we were going to cut. But my y values represents the volume. That was the v of h part. So if I have x-intercepts, what is the y value for all of those? Well, it's 0. well, that means that my volume would be 0. So those are all the places where I would have 0 volume for my planter. So when it comes to creating planters, that would be a terrible value to use for H, right? Because we wouldn't be able to put any plants in there if there was no volume. Right? So what do these x-intercepts represent? H values that give us 0 volume to our planters. All right, so here we got a customer that ordered a particular planter box. So picky customer A here. They want a volume of 100 cubic inches, but they don't care what shape the box is in. All right, well, maybe they're not that picky, right? But they definitely need 100 cubic inches of plants. All right, so how many different heights yield a 100 cubic inch volume? All right, so in other words, where's my Y100? It's a good way to put it, because again, we can let the calculator do this for us. So we come back here, and I'm going to graph another function on the same graph that I started with here. So I'm going to come down here to grab myself a different color, and I want y equals 100. Well, think about what shape that's going to give me. That's going to be a horizontal line, right? Where all my y values are 100. So when I hit graph, it cuts across there. So every place that these two graphs intersect is going to be something that fits this customer's need. It's going to have a 100 cubic inches of volume, right? So where do they cross? I don't know, right? But you know, we can look at this graph and go, oh, here, here, and here, right? But what are those values? It's really hard to tell because the graph is, our window is so skewed, right? But we can let the graphing calculator come up with the answer for us. Right, so again, we go back to second calc, but this time I want to know, let's try that again, second calc. This time I want to know, where do they intersect, right? That's 5. All right, so mine down here at the bottom, it's not asking me for a bound this time, it's asking me for the first curve, right? So I'm going to let this blue one be my first curve, so I'm going to hit enter. And then it very intelligently jumps to the other curve, and it says, do you want this to be your second curve? And if you have got one of these colored graphing calculators, that makes it really nice because it even changes all the numbers to red just in case you missed it. Right? So I'm going to tell it enter, and then it is going to guess again, and it will jump to where they intersect. So one of the places they intersect is going to be 4.8, 100. Okay, so that's one of them. So, oh, we never did answer this one. How many different heights yield a 100 cubic inch volume? Well, there's 3 of them. What are they? All right, well, here's one of them. All right, 4.8, 100. All right, now, you'll notice that it jumped to the one in the middle, and you might want to work your way left to right. That's up to you. The way to make that work is when you go into second and calc, when you're choosing your initial curve and your first and second curve, you want to move that cursor so that it's really close to the intersection points. And then when it jumps to the actual intersection, it'll jump to the one that's closest to your cursor. Right? So I've already got the one in the middle now, so let's pick the 2 on the end. So if I go to second, calculate, and I want to go intersect, 5. Right? This time when I pick my first curve, I'm going to arrow way over here to where close to this intersection. I'm going to go enter, and then in the second curve, enter. And then I tell it to guess, enter one more time, and this time it jumped to the first one. So this one's going to be 0.5 and 100. All right. And then my last one, second, calculate, intersect. I'm going to arrow all the way over here to the right. First curve, second curve, enter. Guess, enter, and it jumps to that one, which is going to be about 9.7 100. Okay. All right, how many different heights yield a 175 cubic inch volume? To save time here, you would do the same thing, except you'd go in and graph the line y equals 175, but I think we can get to the same point here. Do all of these make sense? And the answer is no, they don't all make sense, because we know that there was a limit on what our x was allowed to be. Remember all the way at the beginning when we were talking about what's the most we could cut out of those little squares, and we said that 6 was the biggest. All right, well, that means that this one makes sense because I could cut a 4.8 inch from each corner and then fold the thing up, and I'd get a really skinny planter box, and it would be kind of tall, right? And then I could have this one, the second one, where I've got 0.5 that I'm cutting, so this one's going to be like a really flat planter box, because I was only cutting each one of these H's to be 0.5. But we know that we can't do this one with the 9.6 because that's more than 6. I'm cutting squares that are cutting way more than what I had on that 12-inch side, because I can't cut 9.7 and 9.7. That's more than 12, right? So this one doesn't make sense in the context of our problem. So you got to make sure that when you're doing these real-world problems that your answers actually make sense, and in this case that doesn't. So I'm going to save time and not do this other example for 175 and move on to my last little example here. All right, so we've got an intern. He claims that he can no longer complete the order because he spilled a cup of coffee on the sales ticket. All right, so to me this sounds like an intern that's going to get fired later. And he's also pretty lazy because he can complete this if he just did a little bit of math. So guy that's not going to keep his job for very long. But we need to help Jack complete the order by determining the missing dimensions from the information that's still visible. So there's not much. Apparently this was really potent coffee, and we can't see the rest of the height, the length, the width of any of this. And then we want to explain how it is that we figured this one out. All right, well, all we got is that we know that the base area is going to be 12 square inches. So we don't know the height, that's my x. Don't know the length, the width, or the volume of this thing. All right, so we know that we can use the graphic calculator again to help us, but the only thing that I have this time is the base area. So that's not the volume. And what we already have graphed here is a volume function. All right, so what we need to do is go into our y equals and doctor this up a little bit. So think about which part of this in the y1 graph represented just the base. Well, the volume of a base is length times width, right? So that's everything except for the height. So I can kind of arrow over here and eliminate the height part, and that gets me the area of the base. So I'm getting rid of this x. That was my height. Maybe. Okay, delete. All right, and then also, what do I want that base to be? Not 100. I want it to be 12. All right, so I'm going to graph that. All right, let's take a look at that. So this time, because I only have two x's, I should expect to get some sort of parabola. Okay, there it is. Okay, and there's my 12. All right, so I'm probably going to have to play with the window settings a little bit here because it's really hard to see where those things are intersecting, or not. All right, I can see that it crosses it twice. All right, and I go to second, calculate, and I can go to intersect. That's 5, and I'm going to arrow over here to where it looks like they cross for the first time. I'm going to hit enter, and then enter again. And then enter one more time, and it's going to jump to that one, and it says 5.2 and 12. All right, so here's one possibility for this order. And then if I do it again, go second, calculate. I want the intersection, but this time I want it over here. So I'm going to move over here for my first curve, enter, enter for my second curve, enter again for a guess, and this time it says 9.812. All right, well, both of these graphs, they're representing the same thing, and x is still that amount that I'm going to cut out. So one of these makes sense and one of these doesn't. This one is bigger than 6. So I can't use this graph, right? It doesn't make any sense. So that means that my x, or my height, has to be this one, which is going to be my 5.2. So once I have that for my height, 5.2, now I can start kind of working backwards. If I know that the whole area was going to be 12, then I know that my, well, now that I have my h, I can just take my volume formula and I can plug that in and get my volume. Right? So, I guess I don't need a calculator for that just yet. So that's going to be 18 minus 2 times 5.2. And then that 12 minus 2 times 5.2 times the 5.2. And now I can let the calculator do that for me. So this is going to be 18 minus 10.4, 12 minus 10.4 times 5.2. All right. 18 minus 10.4, 7.6. 12 minus my 10.4, 1.6. So 7.6 times 1.6 times 5.2 is going to give me a volume of 63.232. Also then, my length and my width are going to be those other numbers I got. So my 1.6 and my 7.6. All right, so yay, we helped out Jack. Intern, you're fired. All right, but basically what I wanted you to get out of that was how to use that graphing calculator to really maximize, helping you to be able to find a lot of information. So now you should be able to find intercepts where two functions are intersecting each other. You should be able to find zeros, so where the functions are crossing the x-axes, and you should also be able to find minimums and maximums, all by using that calculation function. Right? So I do not have a homework assignment for you, which I guess makes me the best teacher ever, but I'm assuming that Mrs. Buckold has one for you that has something to do with what I just taught you. So hopefully you're able to do that under my tutelage. If you have any questions, please feel free to come down. I don't have a class 10th or 11th period. I'm located in room 150, and I would be more than happy to help you out.